Hello and welcome to the course Signals and Systems. I am Dr. Zishan Karim from Electrical Engineering Department, CUIUA campus. Let's discuss the lecture contents. In this video, we will discuss how to find the solution of a differential equation, and we will see some examples for to find the solution of that differential equations as well. Okay, first of all, just review what are differential equations. For example, a second order linear differential equation has the form this. P of x is a function, so d square y over dx square second order derivative, q of x first order derivative plus r of x y equals to g of x, where p, q, r and g are a continuous functions like this one. P, q, r and g are continuous functions. In this section, like in this video, we study the case where gx equals to 0 for all x in equation 1. Such equations where gx is equal to 0 are called the homogeneous linear equations. Thus, for the second order linear differential equations, it can be written as p of x dx square y dx square qx dy by dx plus rxy equals to 0. Whereas if gx is not equal to 0 for some x, then this equation will be called a non-homogeneous equation. So, to find the solution of this homogeneous equation, if y1x and y2rx are both solutions of the linear homogeneous equation, as we discussed in the previous slide, and c1 and c2 are any constants, then the function y of x equals to c1 y1x plus c2 y2x is a solution of equation 2. It means that if you have two independent functions y1 and y2, and if you have two solutions y1 and y2, both are the solutions for the linear homogeneous equation we studied on the previous slide, and c1 and c2 are any constants, then y2 we can write y2 equals to c1 y1 c2 y2. So the combination of these two will be the solution of that homogeneous linear equation y of x. So y of x is the solution of that homogeneous linear equation. So in general, it is not easy to discover particular solutions for a second order linear equations, but it is possible if we consider PQR as a constant function. That is, if the differential equation has the form in this way: A, like we replace the P with A, and B with Q, and C with R, right? And they are all constants. So in this case, we can find the particular solution. We can easily find the particular solution of a second order differential equation, and where we assume that A, B, C are constants, and the condition is that A should not be equal to 0. If it is equal to 0, it's not possible to find the solution. So it is not hard to think of some likely candidates for a particular solution. Now we have to think what can be the solution of this differential equation. So we are looking for a function y such that a constant time its second derivative, like a is a constant and its second derivative, constant time the second derivative plus another constant time like b is another constant first derivative plus a third constant time y, which is y, right, c into y, is equal to 0, right? Now we know that the exponential function y equals to erx we, has a property that where r is a constant, here in exponential r is a constant term, and has the property that its derivative is when we take the derivative of erx, right? Then what it results? It results in r into erx, right? It means that a constant time the function, right, is a multiply is a constant multiple of itself, like RERX. Furthermore, if we take the second derivative, it becomes another constant time R square ERX. If we substitute these equations into equation 5, this equation, if we substitute, Like in place of y double dash we will replace with r square erx, and for y dash we will put r erx, and for y we will put erx. So let's see, is r square erx, because already we have a here, br into erx c e rx equals to 0. Now let's take erx common, so then it becomes ar square plus br plus c erx is equal to 0. But you know that erx is never 0, right? Because we have to find the solution, so erx is never 0. So thus y equals to erx is a solution of equation 5. So we can say that for this homogeneous second order homogeneous linear equation, differential equation, the solution of this is erx, where if r is the root of the equation, where we consider r is the root of the equation. So we can write ar square plus br plus c equals to 0, whereas y equals to erx. Now equation 6 is called the auxiliary equation or characteristic equation of the differential equation, this one. So we transform the differential equation in terms of a auxiliary equation in this way. So this and uh, this is the auxiliary equation or the characteristic equation of the original given differential equation. Notice as in an algebraic equation that is obtained from the differential equation by replacing y double dash by r square. So if you replace that y double dash with r square, it becomes ar square, y dash by r, and y by y. So this is the usual way, and I think you already studied some differential equation in your course, mathematics course previously in detail as well. This was just an overview to introduce how to find the solution for a second order differential equation. As in this course, we are trying to write the LTI system in terms of a differential equation. Okay, sometimes the roots are R1 and R2 of auxiliary equation can be found by factoring. Like you have an equation, you need to find the factors, and that using that factoring method you can find the solution easily. In other cases, they are found by using quadratic formula. This is a quadratic formula to find the root, like R1 minus B plus B square minus 4AC over 2A, R2 equals to minus B minus b square minus 4ac over 2a. We distinguish three cases according to the sign of discrimination. Sign of this, sorry, this uh, determinant, right? So b square minus 4ac, this is your determinant. Now, if you have a b square minus 4ac, there are three possible cases. 4ac is less than 0. So is greater than 0. First we will discuss greater than 0. Then for a second order differential equation you have a general solution in this way, C1 ER1x, C2 ER2x. This is the general way of writing first order, second order differential equation for a case when b square minus 4ac is greater than 0. When b square minus 4ac is equal to 0, right, the second case, then you have a general equation C1 ERX plus C2X into ERX. So this will be a general equation for a second order differential equation when roots are equal, b square determinant is equal to b square minus 4ac is equal to 0. And the third case, when b square minus 4ac is less than 0, it is called a complex case. Then you can write the general solution EAX C1 cos beta x plus C2 sin beta x, right? So these are the three possible solutions when the determinant is b square minus 4ac is greater than 0, less than 0, or greater than 0, equal to 0, and the less than 0 case. So these are the three cases. So now on we can find the second order homogeneous equation, second order solution in this way by using this one. Whereas if this is first order, then you know that you only have this term C1ER1x for a first order, because this is just due to the second order, we have a second term. Okay, now we want to express first into the auxiliary equation or the auxiliary polynomial. For example, you have a equation y double dash plus y dash minus 6y. You can write into auxiliary form in this way: r square in terms of double derivative r minus 6, right? So this is auxiliary equation. There are some more examples to give practice on that how to write the given equation in terms of auxiliary equation, because then auxiliary equation using auxiliary or the characteristic equation, you can easily find the root of that equation. So y double dash 2y dash minus 3y, so it's r square plus 2r minus 3, r square plus 2r minus 3. Similarly, r square minus 7r plus 24, r cube minus 2r square minus 4r plus 8. So the roots of the auxiliary polynomial will determine the solution up to the differential equation. So after finding these roots, you can put into the equation like y equals to c1 er1x, right? So after finding these roots, you will put r here, right? Plus c2 r er 2 er2 x, right? So whenever you have r1 r2 available, it means roots are available, so you can find the exact solution of a differential equation. Let's take a first example. Now we have solved the first order differential equation given the input xt equals to ke3t ut. So this is a non-homogeneous type of equation. So we have to find the solution, right? Where yt denotes the output of the system and xt is the input. So this is input, and you can also call the force response. As we discussed earlier, force are the particular response for this input, and the other one, when there this part is 0, we can call it as the homogeneous part, right? Or the homogeneous part. So now we have equation first differential order differential equation dyt over dt plus 2yt equals to xt. As described earlier, we have a for any solution we have a two types: y homogeneous plus particular, where the particular solution satisfies dy d2 plus d2 xt, and in this way we have to write the equation for a particular solution in this way, whereas for homogeneous we have dyt over dt plus 2yt equals to 0. Here we have a 0. So first go for the particular solution. For the particular solution for t greater than 0, right? Yp is a signal that has the same form as xt. So whenever you try to find the ypt particular solution of a signal, then you should write the general equation in the same form as x of t for t greater than 0. So if you write same in the same form ypt, so it becomes ye3t. Now substituting xt, uh, this xt in ke3t ut into our equation. So ypt we have a particular solution ye3t. We generalize that with the ye3t to write the same as our input solution, input signal, right? So we just put these two into our this equation. So it becomes ye3t. So take the first derivative. So it becomes 3ye3t plus 2ye3t equals to ke3t, right? This one. And now cancelling the factor e3t on both sides, because when you take the common, there are 3t here, 3t here, 3t here. So just take common and then it will be cancelled out. So we obtain y equals to k by 5. So that put this value of y in equation 2.36 in this equation, right? So we can write particular solution as ypt equals to k by 5 e3t for the case t greater than 0, right? Now we have now particular solution for this equation, right? Now find the homogeneous solution. So to determine the natural response of the system, homogeneous or natural, we hypothesize a solution of the form as an exponential. As you know that we discussed that we can write c1 e rt right? Because there is only first order, so we have only one term C1 ERT, or we can generalize them C with A and R with S as well. So EST. So it's same meaning as we discussed before. So EST, AEST, right? Now substituting equation 2.39, this one, into this differential equation, where on the right hand side we have a 0. So first take the first derivative. So we have a ASEST plus 2AEST without taking derivative, just put the value of yt equals to 0. Now as you know that this is we can write them as auxiliary form in this way: s plus 2 equals to 0, right? Because they have a no second order term, so only without scalar term we have. So s plus 2 equals to 0, so implies that s is equal to minus 2. With this value of a, s, we can write our equation 3.2.39 for any choice of a as this way, right? So we have a y s t equals to a e minus 2t, right? This one. Now just combine the homogeneous plus particular solution to find the complete solution of a given equation. This one. Because we solved them independently, now just combine. So yt equals to yst plus yt, and we have a homogeneous a e minus 2t, and we have a particular solution uh, k by 5 e 3t for t greater than 0. Because the initial condition on yt is not specified. Uh, as we discussed, we found the previous equation for t greater than 0, but there should be some initial condition, as we already discussed in our previous lecture, that without initial condition it is not possible to judge the overall response of a system. So the response is not completely determined, as the value of a is not known. So we have to find the value of a as well, which is constant, but we have to find. For causal LTI system defined as a linear constant coefficient differential equation, the initial conditions are always 0, which is called the initial rest. As we discussed for a causal system, because causal we don't have an output before time equals to 0, so our time equals to 0. So for a causality system, we can say that y0 equals to 0, which is called, in technical terms, it is called an initial rest condition. So for this example, the initial rest implies that y0 equal to 0. So we found the equation previous slide, that y of t. So now put y instead of t, put 0. So when we put t 0, so exponential term becomes 0. So we have a y0 equals to a plus k by 5, and y0 is 0 because it's initial rest. So a plus k by 5 is equal to 0 implies that a is equal to k by minus k by 5. Now we put this equation in the previous equation, so we have 2k by 5, so we just take the common k by 5 here, so it results in e3t minus e minus 2t for t greater than 0. For t less than 0, the condition of initial rest and the causality of the system implies that yt equals to 0 for t is equal to less than 0, since xt is equal to 0 for t less than 0. So this is our final solution of that equation for t greater than 0. We have another example 2, which is a second order linear differential equation. And for example, we have d square y dt square plus 4 dyt plus 3 yt equals to e minus 2t for t greater than 0. Right? And we have two initial conditions, like y0 equals to 1 and dy0 means the first order derivative is also, when evaluated at time 0, is also equals to 1. So we have two initial conditions as well. So let's start with the particular solution first. So for particular solution, we have e minus 2t here. As I mentioned, that we have to take the same shape as our given input. So we assume that the solution is ypt equals to alpha because alpha is a constant value. To just because here we have a 1, but we have to take the same shape, so we say that ypt equals to alpha e minus 2t, right? Then take the derivative, because we have derivative here, and the double derivative here as well. So take the derivative, it becomes minus 2 alpha e minus 2t. Then we have a second order derivative which becomes, when we take the differential again of this one, it becomes minus minus 4. So it becomes plus 4 for a alpha e minus 2t, right? Now use these equation, this and this in equation. For example, we call that 1, right? So it becomes for a e minus 2t plus 4, because this one we have minus 2a e minus 2, so 4 into minus 2 alpha e minus 2t plus 3 into alpha e minus 2t, which is equal to e minus 2t at the right hand side. To just take that e minus 2t common on both sides, then after solving that we will get alpha equals to minus 1, and then put in this one in, for example, equation 2. So you have a particular solution which is equal to ypt equals to minus e minus 2t, right? This is our particular solution. Now let's find the homogeneous solution. Okay, for homogeneous solution, that equation should be equal to 0, and we you know that for a homogeneous we have two types of solution. For h equals to, for a e r1t, right? We can generally write this solution plus b into e r2t, right? This can be our solution, right? Now we don't have r1 and r2 values, right? So to find r1 and r2, we can just directly solve this by a factoring method. For example, this is our auxiliary. First write into auxiliary term, this equation into auxiliary form. We can write r square plus 4r plus 3 equals to 0, right? So if we further write this way, we can write them as r plus 3 and r plus 1. We can write them as equals to 0. If you open it again, it will becomes r square plus r plus 3r plus 3, right? So when you combine again, it will be same, r square plus 4r plus 3. Now you have r plus 3 here, r plus 1 equals to 0. So as both of them equals to 0, we can write r equals to minus 3 is the one root. For example, r1 is equal to minus 3 and r2 equals to, for example, r1 equals to 1 and r2 equals to minus 3, right? Order doesn't matter, but as we already write here in this way, so it will be easy to understand. So yh equals to a e r1, r1 is minus 1, so it becomes a e minus t plus b e r2t, so it becomes b e minus 3t. So by putting these values. Now for a combined solution, because we have a particular solution and the homogeneous solution as well. So we can write both of them, yt equals to ypt plus yht. So we already find the ypt in the previous slide, which is minus e minus 2t, and then combining with the homogeneous solution e minus t plus b e minus 3t. Now we get yt equals to this complete equation. But here you can see that a and b are unknown. So to find these unknown, we will focus on our boundary or the initial conditions. So we already given two initial condition, y0 equals to 1, and the second first order derivative related at 0 is also equals to 1. So using this initial condition, we will solve this equation. We will further evaluate this equation to find the value of a and b. Okay, as given y0 equals to 0, so put in the previous solution, when we put previous equation and we put y0 equals to 1, it means that y of 0 is 1, so left hand side becomes 1, whereas for other terms a plus b minus 1, and which implies that a plus b, just rearranging, is equal to 2. So we named it as 1 here. Now take the first order and derivative of the previous equation. We can get minus a e minus 3t minus 3b e minus 3t plus, due to this negative sign already we have a negative sign, so negative negative to plus e minus t. Now you know that y dash equals to 0 equals to 1, right? This is our initial condition. Using this initial condition, 1 equals to, put 0 here, put 0 here, put 0 here, it becomes minus a minus 3b plus 2, right? Sorry, there was a 2t here as a type, right? So plus 2, right? Now rearranging, so it becomes a plus 3b equals to 1, which is equation 2. From 1, equation 1, using this equation, we can write that a is equal to 2 minus b, right? Because just rearranging. Now uh, we can put this in equation 2. So instead of a, we put 2 minus b plus 3b equals to 1. So it becomes 2 plus 2b equals to 1, b equals to minus 1 by 2. Now put this b equals to minus 1 by 2 in equation 1. So you can get a is equal to 2 plus 1 by 2, which is 5 by 2. So we have a final solution. We have a final homogeneous solution in this way. Y s t equals to 5 by 2 e minus t minus 1 by 2 e minus 3t. Because now a and b both are known. This is a and this is b. And if you combine, like we have a combined solution y of t, so just put y of t equals to, you can write in this way, this one, right, plus minus e minus 2t, because already we find the particular solution. So this term minus this term is our complete solution. Thank you for listening, and for question answer session there will be some reserved slot, so exact time will be communicated later on. Thank you.